My pleasure to introduce STM, who many of you actually know, or should I use those? For those of you who don't know, Tim is a researcher at Microsoft Research and Cambridge, and he has been over here for about a month now, working with Singularity and Bartok on integrating the software transactional memory work that he's done into our runtime system. And I think I'll talk about the work he's done with a bunch of people here. And, I guess this is pretty much the end of your visit.
Yeah, flying back tomorrow afternoon.
Yeah, so he's escaping, but he's certainly going to keep on our collaboration. I think it's absolutely really well. Yeah, I'll get back there.
Okay, that's impressive. There's some work I've been doing in Cambridge for a few months now, and been really focusing on in the last month. Well, I've been over here working with Mark, Harvey, and David on putting this into Bartok. It's very much still work in progress. I've got a few initial results at the end of the talk, and I'll talk about a few of the ideas that we've had but not yet got down to implementing. So if I was trying to write this up in a conference paper at the moment, it would have to be in that furious tense that you use to try to give the impression that you've done more than you actually have at that point. But I'll try to make sure that I'm honest about where we are at the moment, what's still to be done. So the goal in this work is to provide an implementation of atomic blocks as an easier to use way of controlling concurrency in multi-threaded software. So the basic language aspect of this is that we want to be able to bracket any piece of code accessing data in shared memory with an atomic block, and have the runtime system and the compiler be responsible for ensuring that that code runs atomically with respect to whatever other threads in the system are doing. Now that's an idea that, of course, dates back to the 70s, and the novelty in this work is really trying to push forward the performance of the implementation so that it's a suitable thing to use on general purpose machines. And that's motivated by the emergence of multi-core processors and the fact that we'd anticipate that more and more machines are going to have hardware support for parallelism. So we need to find more sources of that parallelism within application software and make it easier for mainstream programmers to write parallel software correctly. So the main problem that I'll talk about is performance in this talk. I'll come on in a bit to some of the other problems that exist, but here my focus is performance. And the challenge in making atomic blocks run fast is that a naive implementation of them imposes lots and lots of overhead on all of the memory accesses that are made inside the atomic block. A typical implementation starts off by cloning all of the code that runs inside the block, and then interposing on all of the heap accesses it makes in order to tell if that thread is accessing data that's being concurrently accessed by other threads. Typically, the thread runs and builds up a private log in which it records all of the memory accesses it's made inside the atomic block. And then only at the end of the block does it go to the canonical version of those objects in the heap and check whether anyone else has made modifications concurrently with it, and therefore whether the atomic block can be committed to the heap or whether it has to be thrown away and re-executed. So it's fairly clear that this adds some substantial overhead to the program, because whenever we touch memory, we instead have to go to our log, find out if we've already logged an update to that location, and return that updated value. And whenever we write to memory, we have to go to the log, allocate space for the new entry in it, and store the update that we're making. So each memory access turns into perhaps half a dozen or more memory accesses. It triggers the potential for garbage collection, perhaps, and so the end result is maybe a slowdown of a factor of 3 or 4 if it's done naively, each time memory is touched. So the research challenges in speeding this up are trying to avoid... This on the left is supposed to be a can of worms, which I hope isn't a UK phrase. The PowerPoint clip art unfortunately has legs on the can of worms, so I got rid of the legs, but they don't really look much more like worms. So we'd like to avoid some of the aspects of the naive implementation that contribute majorly to its cost. Okay, one of these is that we want to make reads and writes be able to work directly to the heap when running inside an atomic block, so that when we do a read, we don't have to go and search our logs in order to see if there's been an earlier write that we need to return. So we want to get rid of this searching step during atomic read. We also want to try to make the system more streamlined in terms of how objects are represented. Some of the proposals for implementing atomic blocks add extra kind of levels of indirection to every object. So instead of a field read going to just an offset from the object pointer, it would have to follow through one or, in some cases, two levels of indirection before it gets to the copy of the object state that it's supposed to be reading. That, of course, adds to the performance costs. We want to avoid schemes like detecting contention between threads based on hash values. There was an earlier piece of work I did with Java where when different atomic blocks were running in parallel, we'd detect whether they conflicted based on hashes of the addresses that they accessed. And that worked fairly effectively for some cases, but it was kind of this nagging doubt that there might be cases where we get a lot of hash collisions and the performance would really drop off poorly there. We'd like to keep the operations that we execute fairly simple so that the program can understand where the costs are going to be incurred and where conflicts will occur and where they can be guaranteed not to. And finally, we'd like to make sure that when we're running short transactions of only 2, 3, or 4 memory accesses, that we don't have to do memory allocation. Some systems required that transaction logs were allocated each time a new transaction started. And so a program that looks like it runs in constant space would turn out to churn through memory and create a lot of garbage in the reclamation of those logs. So we'd like to stave off allocation as far as possible. Now, that's the first aspect of performance. Then, looking at a higher level, we've got another can of worms to deal with, where if you look at an application and think through what logging needs to be done within atomic blocks to make it thread safe, we can actually avoid a lot of that logging in principle. So, for instance, if a thread enters an atomic block and it allocates a new data structure, then we know that there can't be conflict on that data structure because only the allocating thread has access to it until the atomic block commits. A naive implementation doesn't take account of that kind of features, but it's one of the key ideas we'd like to explore. Another area where we can really slim down the amount of logging that the transactional memory needs to do is when we're making a lot of updates to, say, memory locations. We don't want to have to keep logging that we're accessing a given location inside the atomic block. We'd like to just do that once at the start of the block, and then we've got all the information we need in order to detect conflicts. And finally, we'd like to be able to just pick up some of the standard compiler optimizations and apply those to the implementation of atomic blocks. I outlined earlier the general idea that we have a log that records the access to the made, and that when we add to that log, we have to allocate space in it, bump up a logging pointer. We'd like to be able to amortize some of those costs over multiple stores into the log so that we don't just have that written to work. And we can do that, as I'll say later, by exposing the logging operation at the lower level and enabling compiler optimizations to combine some of those steps where we've got multiple stores into the log. Now, in this talk, I've said I'm going to emphasize the performance questions of atomic blocks and really have in mind the goal of seeing how fast we can get atomic blocks to run purely in software. But of course there are a whole load of other problems that would have to be solved before atomic blocks would be ready for use in a mainstream language. One frequent source of discussion is what it means to have nesting blocks, what exactly the semantics of those are, when perhaps an inner block doesn't connect to an outer block, does that get forced to the port or not? There's the question of what happens with exception. We raise an exception in an atomic block. Does that mean we undo all the things the atomic block did with a kind of all or nothing execution model? Or do we say that exceptions and concurrency are two separate problems and have some mechanism like the try-all blocks that Darby and David and Mark worked on last summer to deal with rollback into exception cases? We've got, I don't mean to denigrate these by making them small, but they have slides. The problem of contention management. If we have a large number of transactions, then we want to make sure the system makes progress, but they don't end up smashing against each other. There's some good work at Rochester that we hopefully can pick up to address that issue. The big semantics issue is what happens if you have some I/O in an atomic block. I'm really looking here at just memory, and so of course, what happens when you try to send data on the network, reading like the files on disk. We need to think of those issues. And of course, another big problem is the lack of good workloads for evaluation. We've worked on some of these language ideas and the implementations of them, but we don't yet have big programs that are built using these constructs. And so we don't have a good idea about perhaps whether atomic blocks are going to be 10 instructions long, 100 instructions long, or 10,000 instructions long. We hope that this work will, although not directly addressing these other issues, will help enable some of them to be looked at in the future. So by trying to provide this system as part of Bartok and providing it to Singularity as well, we hope that people developing applications to Singularity will be able to apply atomic blocks as the way of structuring the concurrency between threads within a transaction, and we'll get somewhere with this study of what workloads might be. And that once we've got that and got some experience on using atomic blocks, it will help inform the decisions on a lot of the other language design issues and the ways of integrating these other problems in a full solution. So in the rest of this talk, I'll go through the system at two levels. The first level will be what the Bartok compiler does in taking source code using atomic blocks down into operations invoked on a transactional memory for logging the access that's made in the block and for therefore enabling protection of contention between blocks. I'll then look at the lower level, what the runtime system looks like, how we modify the layout of objects in memory so that they can be manipulated in atomic blocks. And then I'll finish by presenting a couple of initial results taken from synthetic benchmarks and some of the spec tests where we've simulated or what might be done in larger programs. And the work here is based on the Bartok compiler and runtime. I'm sure many of you are familiar with that, but just an overview, it takes as input application code written in MSIL and runtime system, which is also written almost entirely in managed code and compiled to MSIL. So it's providing us an opportunity to do a large range of optimizations that are able to take into account both what the application code is doing and also optimization alongside the implementation of the transactional memory. So that provides an ideal framework for experimenting with this question of performance. If we can't get transactional memory and atomic blocks working well in this environment with optimization and combination straight to native code ahead of time, then that suggests it would be impossible in other environments or limited resources like a JIT compiler. And conversely, the experience we gain here of doing optimizations that aid atomic blocks and developing transactional memory implementation techniques if we find good solutions to these problems, we can hopefully identify ways of making those fit into the Linux source environment. The overall structure of the system then is that the user writes code using atomic blocks. The compilation process is responsible for turning these into calls on the STM runtime that is also feeding into the compiler. And then the STM runtime is designed to enable a range of existing compile optimizations to be applied to the operations that get produced. The design of the interface to transactional memory that the compiled code is invoking is set so that it tries to avoid preventing the existing optimization work the compiler does. So that means that we leave all of the data accesses within transactions in exactly the same format that they are in existing code used by Bartok. So when we read or write to an object, at the stage where we actually get the data or set the data in that object, we're just doing a store relative to the object pointer. We don't have any extra levels of indirection that the compiler has to be aware of. So we're still able to use the existing optimizations within code compiled in atomic blocks. The constraints that the STM runtime imposes on the compiled code are that it has to add additional operations in to indicate which object is accessing in the atomic block and which fields it's updating. And these are really the key pieces of information that the runtime system needs in order to ensure atomicity. It needs this log of which locations are going to be read from and updated in order to protect function between two atomic blocks that run in parallel. And it needs a log of the contents of memory that gets overwritten by execution in the atomic block, so that if the transaction doesn't commit, we can roll back memory to the starting state and try the atomic block a further time in the hope of avoiding contention in the second execution. Now, during the compilation process, we go down through introducing these additional logging operations at a number of different levels. So I'll go through the different levels involved in the compiler and show what the source code with atomic blocks in looks like, and then show how that translates into the explicit operations on the STM runtime as we progress down towards native code. Now, the starting point is the input in MSIL with atomic block boundaries indicated in it. We do that at the moment by having a stylized kind of try-catch block, where if we have a block that captures a particularly named exception, then the runtime or the compiler knows that that is indicating an atomic block. This lets us avoid having to modify the C# compiler to support atomic blocks explicitly. Just replace atomic blocks with this notation. Now, the next step during compilation is to convert the MSIL into intermediate code and to clone all of the operations that execute inside atomic blocks. So we're going to end up with two copies of the code that's in atomic blocks. One for if that code executes normally, and the other for if it executes within an atomic block. And that lets us avoid introducing costs to code that's just running directly. We can deal with the atomic case separately. In this first step, we have the normal intermediate code that Bartok produces, but we have these additional flags on each of the operations, saying whether they are accessing objects for read access or for update. So the original code was comparing field values and seeing if they were equal or not. And so the intermediate code for that translates into two instructions that access fields from an object and then a comparison. And we add this in this read tag that says that the object that we're accessing those fields on has to be added to the set of objects that the transaction is read from, and that we therefore need to detect conflicts on. Now this level in the intermediate code is where we could do a number of transformations. So for example, if we knew that the objects being accessed were one that had recently been allocated, that had been allocated inside the atomic block, then we could safely strip off the index read markers on the instructions and just access them directly without the cost of putting the entries of the log. The next stage during compilation splits out the operation to make explicit the calls on the STM runtime. So instead of having an operation that combines the field access and the addition of an object to the read log, we decompose it into one instruction that adds the object read from, and then a second instruction that actually does the data access just as it would outside the atomic block. So those two field accesses turn into two pairs of instructions, adding the objects involved to the read log, and then getting the data from their fields. Now, at this stage, we can do a further set of optimizations on the code. And for instance, if we were accessing two fields in the same object, then we'd have two of these in this object read instructions, both specifying the same object. And we could see that the first one will precede the second and eliminate the second call in the case where they were both acting on the same object. Yeah.
You can imagine you listed fields for reads as opposed to whole objects, but then of course you wouldn't be able to do this particular kind of optimization. Is just the reason you chose to list whole objects, or is there another reason also?
Well, there were a lot of trade-offs about whether to detect contention on fields or on objects. There's a possibility that you introduce contention by looking at whole objects. But the downside of looking at individual fields is that you lose the optimization opportunities where you access lots of fields on the same object. And you also end up with additional costs of runtime where you need to keep you need to have data structure that can detect contention at that finer level. The implementation techniques we've seen really kind of work naturally, where you add information to object headers to detect contention. I think it would be hard to develop techniques that would have the same straight lines to working up.
And this works well anyway in terms of false.
And I think there will clearly be cases where there are false conflicts. A good example there is a large array, which becomes a single object from the point of view of the network. But it's a model which I think can be explained to programmers that they don't touch the same object from multiple places at the same time. And so I think that's an easier mental model to have about how this works than, say, if we work with fine granularity and perhaps a byte array or Boolean array where we then end up with some other false contention.
You would actually also run into problems if you're accessing fields that are smaller than the natural word size, which most machines don't provide atomic operations. So you'd actually have to do a read, block, modify, write, which would be expensive.
In the commit page.
At some point.
Yeah. These are ordinary reads and writes. Here are the ones.
They'd have to be atomic speed modified. So at this stage, we can hopefully strip out a lot of redundant index operations. We've got some conventional about number later on showing the extent we get there at the moment. Then the final step decomposes the operations further. So instead of just having an operation, say, add an object to the read log, you split it up into an operation to get hold of the current thread, to get hold of a structure that contains points to the read log, and then in future work, an operation to reserve space in the read log for these two additional objects to go into it. And then finally the two stores into the log itself. So this is moving it to the level at which the actual interface exposed by the actual runtime operates. And it exposes further chances of optimization. In this case, we have two in-list object operations, and when we go down to the lower level, we can just initialize the operation stage once and amortize the cost of that over the two log operations. We just need to get hold of the log once, check there's basically two entries, rather than get hold of it twice to do the checking on a per entry basis.
This is being done dynamically, right? So I was curious if you could do some analysis to identify all the objects being touched in a particular block, and then enlisting all of them at the beginning of the atomic block, basically. Is that a reasonable thing to think about?
This is being done at compile time.
Right. So but these are individual operations on each object as the block executes. And I'm just curious if you could do sort of a single operation on all the objects on the sequence.
We could do that. I think we already get almost that.
Oh, okay.
For very simple.
You eliminate most of the redundancy anyway.
So, yeah. The difficulty is where the redundant accesses are very far apart. You then need some support of genuinely runtime effects of redundancy. But we're already getting a factor 2 reduction of redundant logging as far as the optimization so far.
Just on that though, presumably a problem is to statically discern all the objects that would be manipulated by an atomic block would be a block that decides computationally what object it's going to manipulate. Like, feel like a hash table, right? And so first you have to log a hash table, it's got a whole bunch of stuff in it, and then you decide you're going to look at a couple of them, right? And statically, it's not clear how you could ever, say anything other than you would need everything in the hash table defensively, which isn't clear.
Yeah, you have to see how they're being used.
Yeah.
And I'd expect that in cases where the code would like the little atomic block, say, to change the value to fields, then we'll already be getting a good way towards dividing that down to code, approaching what a manual version would do. We open two objects at the start of the block, and clearly only have to do getting hold of the log.
So for straight line execution, you can hoist quite a bit of this.
So, after looking at the different levels of the code goes to during compilation, we're following a kind of three-pronged attack to reduce the overall runtime that code is on the block. The first step here is to reduce the number of times that we have to do index calls and log calls. So these are the optimizations we do fairly early, where the index haven't yet been broken out into component stages. And we'd be thinking about removing duplicate calls to write to the log, and using code motion to perhaps try to move logging operations out of loops, and perhaps to enable further combination of unnecessary logging. So the second strategy is to try to amortize work that's done within existing log operations. Getting hold of the log once, checking that there's space for a batch of writes into it, rather than doing the checking on every single time you go to the log. We haven't really got very far on that middle span yet, in terms of the log files I talked about. And then the final strand is trying to make sure that what remains runs as fast as possible. So designing the runtime system so that the fast parts to writing to the log are not going to not going to be very cumbersome. Make sure that they don't fill a lot of data on that they're amenable to inlining, if the inlining part and the compiler decides to do that. So I've got a couple of examples now taken from some benchmarks just illustrating the kind of optimizations that we can do. And then I'll go on to look at the final part and see what the runtime system does to try to make the logging and the transaction commit streamlined. The first example comes from the Lisp interpreter inspector. And we've been using this as a model for what a very large atomic clock might do. The Lisp interpreter runs a series of scripts passed in the command line, and we've modified it to run each script in a sense of atomic clock, and so millions of instructions within the atomic clock. The Lisp interpreter itself is fairly complicated, and it's built its own garbage collector, which is collecting space of objects that are created as sharp objects in the heap. And the example code here is from one of the hotspots in the Lisp interpreter, which is its own garbage collection function. And the example shows where we've got some code that using object vectors up here, X down this, then making an update to a field in it, and then doing a read and write to another object vector previous. And in this kind of case, the naive code that we'll get from the compiler will put a call for here to open Feb for read access, then it'll do a read, and then it'll call again into the STM to open Feb for update access. So what we'd like to do here is to see that we have this read to update upgrade going on, and to just open Feb for update at the start here, and avoid having to do too long operations. We could probably do some more to this code as well. For instance, the Excel list object here is probably being accessed down here for a read modified write. And again, we'd like to open it to write just once, rather than having to open it to read and upgrade. Another example from a note in the sector is that we often see methods like this one, which is to do with some portion of computing the next move in the game, where we almost first step in the function make an access to a field in the current object. So at the moment, we'll compile this code, and the first operation in it is going to be to open this read access from the get border array application. What would be nice would be to do some kind of neededness analysis and to infer that whenever we call player pos, we need to open this parameter update, and then to push that back into the call sites so that they open its update before calling into player pos. And that could be an important optimization because it exposes that earlier open call in the caller to this to other optimizations. It might be inside a loop. We can then hoist it out of the loop, or we can pull open calls out of multiple called functions and open the object just once before this serial call. So that's an optimization we've got in mind for experimenting, but it isn't one that we've yet got in practice. Now I'll turn to a quick overview of how the runtime system works, and we'll then look at some of the performance numbers. So the way that I'll describe the runtime system here is the way that it's implemented at the moment, and the way that I think makes it easiest to describe the structures involved. We've actually got some new ideas to avoid some of the overheads that the system is going to impose. But the system I describe is consistent with the system that we have the measurements for later. The basic idea is that we add 2 extra header words to each of the objects and use these to detect conflicts between concurrent atomic clocks. The first header word is used as versioning, and it holds count of the number of times that we've updated that fields in that object inside an atomic block. And we'll detect conflicts by seeing that a version number has changed between when we started a block and when we commit the block. Of course, it's the addition of these header words as the main overhead that we're working towards eliminating. But showing it here helps, I think, to explain the algorithm. So we have two objects here, and structure down to the left is is related to thread A, which is going to form an atomic block with access to two objects. So thread has three separate logs associated with it that hold, in the first case, a list of objects the transaction is read from. In the second case, a list of the objects which are updated. And then finally a list of the updates that it's made so that those can be unwound if the blocks are born. So the read log consists of a list of chunks that are going to contain pointers to the object read from, and a snapshot of the version number that the object held. So in this case, the thread reads from object 1 and object 2, and so initializes the read log that goes with pointers into the object, and the snapshot text stores version 17 and as a store version 42. Now you'll notice that those read operations are not having any effect on the shared storage of the system. And so if we have a multiprocessor machine, the locations holding the actual object state will remain in shared mode as far as the caches are concerned, rather than turning what looks to the programmer like a read-only operation into one that's dragging lines around the memory system. The list of objects open to update has a similar structure to the read one, except we need to use the second field in order to detect a certain kind of conflict. We'll come on to in a moment. So when adding an object to the update set, we do have to reveal that to other threads, and we leave a marker in the object header saying that we've opened it and that it's now currently being updated by thread A. Now the second stage of opening something to update is to store a copy of the version we used to have in the second header word. And the reason that we need to store that version is that it will let us detect during a commit operation whether a transaction is valid without ever having to search the log. And avoiding searching is one of the motivations that I've had a way of getting it before. We'll see the example later on to clarify that. Now the third log holds the list of overwritten values so that we can roll back the execution of the atomic block if intention is detected. And there we have pointers that identify the object being updated and the value that we've overwritten. And we then make the update directly in the session. So you'll notice that this design means that all of the mechanism needed to detect conflicts and to recover the transaction rolls back is held up to the side of these logs, and that the object field values held directly in place, so they can be updated by ordinary writes, they can be read from by ordinary reads. Yeah.
So, object 2 in this example is an object, it's not a field, right? In particular, if it were very large, if it were an array or something and we wrote some value to it, the overwritten values log needs to contain a snapshot of the entire value of object 2?
It does, in fact, because the log system, when an object is open to read log update, refers to the entire object. But the log of open values just refers to the location of.
So if I write just a word into it, that actually includes, well, you wrote to this offset, this value. Okay. It doesn't sound, okay.
So the size of the overwritten value log is about 3 times the size of the amount of data you've written. Because each of those little blocks has an X pointer and a pointer to the word, and it's per word.
Right.
The logging implementation is more, I think the answer is yes, it's 3 times more, because you have a pointer to the old value you're required to be able, or you have the old object, you're required to be old object. We use a much more sophisticated mechanism for representing the list. So the lists are broken up into chunks of arrays of a list of arrays, and you keep chunks in them. So it's
more like 2 times that.
Is there a third thing you have to keep in?
Well,
Is it-
it's not quite. It isn't. There's the worst case if all of the right distinct locations would be, I think we get it to be a factor of 2.
Oh, you can coalesce those as well.
And if we have duplicate slides, then we only need to log the first one. And say in the case of slides split field, we only need to log say the word one rather than the subword. So in terms of the bound, it could be a thing that itself, not a multiple of that. But that's really unavoidable because we're providing mechanisms that control that the updates and we need to have enough before.
If I have an accounting block that overwrites a value 1 million times, will I have any entries in that last log?
In the current implementation, in all probability quote, that it's based on is the text deployed.
So there is some work done at one time to determine what the
Yeah.
is.
So the general idea is that we have the code that writes the logs run quickly without the text. On the assumption that many atomic logs are short, and so writing
And then you press blocks as soon as they're all blocks.
Yeah, then when we fill a block or when we do a garbage collection, we do a small amount or a bigger.
So you only do the line there.
So let's say now that the transaction does commit, making updates to the object. The first stage of that is to go through the objects in read from and to make sure that they have still got the state we're storing. That is, making sure that no one else has got it after we read the object and to make an update. And then the second stage we go to the object we've updated and mark as no longer open. Now, in many cases, checking that no one's conflicted with our read is straightforward. We look at the version number that we've got in the log, we look at the version number in the object, and we see if they're equal. If they're equal, no one can commit because you have to increase the version number. So option 1 is okay. Then for option 2, you see why we need the same version number of 42 in there. Because we can't compare the 42 in the log against the value in the first header word, because we've lost the version number when we revealed that we acquired the object to update it. So we do the comparison between 42 and the saved version number in the header, and that protects again that no one got in there between our read and bumped it up to 43 before we opened the object to write it. So, and as I've said before, the scheme as described here has a lot of there's a lot of implementation issues rather than the way we represent the header words and the exact structure of the log. But I hope it gives a flavour for how the structures work. And I'd be happy to discuss in detail with you.
Can't generally tell ahead of time whether an object will participate in a transaction in transactional semantics. Do you add these 2 fields to all objects in the system?
Currently, we do. But the idea is that we all use the same kind of thing, so generating blocks. So if we have an object that is only participating in transactions, never lost, we can use a multi-use word in the head of that. If it's locked and it participates in transactions, then we have to have a larger structure. That word points to tells how it's communicated.
So when you run object 2 its own, at that point when you copy the V42 down to the save space, you check at that point to see if it matches, and at that point did you know you own it?
We could check there. It may be just in some cases that it helps us check early by doing that check as soon as you open the slide. But the problem with that is that we have to search the read, and the read log potentially going to be much larger than the set of objects listed. So it might be interesting to look at having some kind of hashing tool that lets us try to look at the read log quickly and with some probability trying to do it if we've got a problem already. But I suspect that the cost of those on the read would be higher than the savings in the section.
One more question. During a garbage collection, do you have to go and do the compaction? Do you have to lock these locks?
So that's actually something that we talked about this morning. The current scheme treats the logs as loops, and so we'll fix up these points the collection happens. If this was a point of value field rather than a scalar, then we keep whatever we've overwritten. And we can easily extend that to deal with generational collection by having a kind of high watermark, how far we scan the previous full collection. The downside of garbage collection in that scheme is we might start an atomic clock, create a load of garbage that ends up being reachable from these logs, and then not be able to claim the garbage at the end of the atomic clock. So what we're hoping to do is to have this more integrated with the collection so that we can detect objects in these logs themselves as garbage and reduce the size of the logs that has So this is really going.
How would you know that some object inside the log is garbage?
So what the garbage collection needs to do is to make sure that all the objects within the kind of post-net stage of the transaction account, and all of the objects will be reasonable if the transaction rolled back also count. So we need to keep information at runtime about which objects have allocated in the transaction and which ones were pre-existing, and detect where it's probably better to stage offline if it ends up getting into the block. We kind of convinced ourselves the teamwork of
This is just a detail, but I'm curious when you update OBJ2 for enlistment, or when you enlist for update, won't you, at that point, don't you know that at some future time you're definitely going to want to write to the object? So you might as well check the read log to see if transaction fails right there?
If we wish to know if there's a conflict, then potentially the read log. But if there's a performance question of whether it's worth uncertainty.
But at the time of commit, after which you might have done much more work, which was fruitless, right? You definitely know that you'll need to look in the right log then.
But we, at the commit, if you just learn log swap, there's never
I see. It's more efficient to do the reading.
In the absence of contention,
I see. Okay.
Whether
So the total cost if you did the check at every update enlistment for all of the objects would be considerably greater than if you just did it in bulk at the time.
There's a question of whether a particular workload makes sense to make one book in that space or another. Right, it's essentially an optimistic process. We're crossing our fingers on that one. We have the contention management council problem. Okay, now I've got a couple of slides on some of the detailed problems with the commit operation. I'll skip over those just so that we get on to the results that are more generally interesting. But just to highlight some of the problems that we haven't brought up. You might worry about what happens with version numbers when they overflow, and again, what happens to that future density in the log. Dealing with version number overflow is actually easier than I'd initially feared, and we can do it in fact by making sure that at least one garbage collection before you go through the entire version on the stage. And so that means that we need at least one garbage collection to have 30 atomic clocks to start. And a nice thing about the design is that the garbage collection doesn't have to traverse the entire heap. It just needs to traverse the objects that are involved in transactions at the time the garbage collection starts. So and that was a nice observation. Now, the initial results here are, as I said, fairly preliminary given the absence of better ideas about workflow. The method that I've taken is to look at the slowdown introduced single-threaded code when it's running inside an atomic clock. So the baseline is running a piece of code directly without any support for concurrency control. And we compare that against putting it in an atomic clock and look at the overheads that logging introduces, and then the benefits of the optimizations that we've already implemented are able to claw back in those tasks. Now we've got two sets of tests. One are small synthetic control programs, get this red laptop. And in these cases we have short atomic blocks that make a few dozen accesses to memory. And we're interested in seeing how fast we can make those kinds of blocks. Those are the ones where future hardware may support transactions, and so we need to know whether we can do what kind of overhead we have purely with software, and what kind of hardware support would make sense, given the observations we have about the costs to make. And the second set of tests are large programs where we have atomic blocks that span millions of instructions. And for these, we've taken spec tests and wrapped atomic blocks around either the entire body of the domain or around significant work. And these are cases where we wouldn't expect hardware support for complete atomic execution, and where we need to think through these issues like how the garbage collection works while inside the atomic block. Now the status of the implementation is we have a large number of these optimizations I've talked about implementing. I should say benefits of that work with data marketing and arguably been doing. We've got support for keeping hold of the logs between the disciplines to avoid that work. We have support in CSE for identifying redundancy in disk operations, logging operations, and eliminating many of those. With some support for pointing out loops, where we have a loop with access to the same object many times in transactions. We've got an initial version of the combination of reads and updates to avoid upgrading and to cut down the number of disk calls. And we've got some information on the compiler about the level of contention that the runtime system detects access to static fields. So that it combines in this call that on static fields are going to be treated as conflicting runtime. Now I do have some more experiments or notes of experiments about the future contribution to different optimizations here. But I've got a kind of general overview on the slides here about where they're working. The first result here is looking at the performance of their laptops, where we have a benchmark that does 100% duty cycle operations on their BlackBerry, picking operations biased towards inserts biased to searches over lookup, over insert and delete. And the program runs in a tight loop, working on a key space of, I think, about 2 we get failed. The y-axis here in the bar is showing the total runtime, and the grey block at the bottom represents the time taken running this with a single thread and no concurrency control, and that's about 5.1 seconds. The entire height of the bar represents what happens if we add in support for atomic blocks and we don't have any of the optimizations enabled. So that would be the kind of performance that a naive implementation would get if it used the STM runtime system that we've developed. So As a portion, that's perhaps coming on a factor of 3 slowdown if we go for the naive, non-optimized case. The blue sections are showing what the overheads are in supporting atomic blocks. So the time that it takes to run the benchmark with each operation in an atomic block is up to here. And that's a factor of 1.9, that's a bit less than a factor of 2 slowdown on the single-threaded case. Now, within the sections, we can break down what the different contributions are to the cost. The results within the atomic block are perhaps surprising, looking at where the costs are incurred. The sliver here is the cost we get for adding the extra 2 header words to all of the objects. So that's 0.4 seconds, coming on to 10% of the time that the single-threaded version took without the header words. So we'll hopefully get a good improvement when we move to a system that doesn't have extra header words introduced. The next block here is the one that I find surprising, and that's the time that it takes if we add in calls to the transaction manager to start transactions and to commit transactions as we enter and leave the atomic block. Remember, we haven't yet added in any of the logging operations. These are transactions with no data access within them. This is just showing the cost of the bookkeeping done on transaction entry and exit. So I hope that this block can be almost entirely eliminated by looking at what's going on inside the start and commit calls and making sure that a cost isn't incurred there in the case of empty transactions. The next 2 blocks are the ones where I would expect there to be costs. The one here labelled prepare to log is looking at the cost of everything up to the stage where we actually write into the log. So computing the address we need to log, getting hold of the address of the object header that contains the version value that we're going to record. So that takes normally 7 seconds, what over 10% of the baseline log. And then here we've got the actual cost of writing the log, about 50% of the baseline. And this, of course, is really capturing 2 things. So the cost of writing the log itself, and then there's the work generated at commit time of checking those log entries. So I don't unfortunately have a breakdown of those, but hopefully the cost of writing to the log can benefit from future work on amortizing some of the steps there.
Yeah. So this is the case where there's no contention?
That's right.
Okay. And have you looked at all at sort of, sort of ramping up the contention?
I haven't here. I've got a dual processing machine back in Cambridge, so that's one of the next experiments to do. I would hope that if there's no contention, then we don't get any extra costs from having multiple threads, because they're not ever trying to access the data.
But you're using the compare and swap thing already, so you're basically paying the cost of that.
Right, this is all safe for multiple threads. And the green blocks at the top are showing the benefits that we get by 2 of the optimizations here. The first one is reusing the reference we have to the structure that has the logs in it between calls to inlet operations. And then the top one is doing CSE between those calls and logging operations, and so getting rid of some of the redundant log entries. So overall, with red black trees, we've got some costs that we'll be able to slim down here, and hopefully 2 blocks here that we'll be able to eliminate almost entirely. And so I'd be fairly confident that we can get this down to about 50% overhead on single-threaded execution. If we look at the data that remains in the logs, we don't actually have many duplicates left. So the optimizations here are doing almost everything they can to avoid redundant logging. Now we get a quite different picture looking at the list interpreter. The overall result that it runs slightly less than 4 times slower than with just running it directly. And so I think this is the first time that anyone's looked at running transactions manually with non-trivial size transactions. It's pleasing that it doesn't grow exponentially or even quadratically with the number of data accesses being made. The runtime, as I said, in new processes is 2.5 seconds. If we enable the optimizations we have so far, then it's just over 6 seconds. If we run it in the naive test without optimization, then again, we're getting a good improvement in the optimization. It goes up to 11 with every phase. The numbers at the bottom, though, are showing what opportunities remain for optimization work. These are looking at different functions exposed by the transactional memory and account for the number of times that they're being called. And those are necessarily in units, and these are all in millions. So the calls in this object read and in this object update are the main ones where we add to the read log and the update log. And you can see that with optimization disabled, we have 146 million objects open to read. And then the optimization set that down by about a factor of 2. We do similarly well for update. But the bad news is this figure here, the number of log entries that actually have to be written to the log because they're non-duplicate. Of these coming on to 90 million calls into the logging function, we only actually write 300,000 entries to the log. So we've got a massive number of people who can still go through, and therefore a good opportunity to develop optimization techniques to avoid those duplicate calls into the log. Okay, so
do you have to measure the space overhead?
I was trying doing that this morning, and we run the program in both of these cases with the same PC setting, and the logs go into the garbage collector. So it's not as if we have got some space free in the we certainly add a lot of pressure to the logs themselves in XLS come to about, I think, 3 megabytes by the time that the transaction comes to submit. And a lot of the entries there relate to objects that are already dead by the time the transaction commits. And so, of course, not just of the log itself, but of the garbage that it's needlessly retained. So, I think that we're getting down to space overhead here. It's one of the big things to do there. I'm afraid I've already gone over time, so let's finish off with a quick data to work. As I said, we've got lots of ideas of optimizations that look like they'll help the hotspots within the benchmark we've looked at. And there's a lot of work still to be done on experimenting with those, checking if they work in practice, and seeing how far down we can get the log size. We've got this checked into our code, and Arden's working on getting that singularity, I think, real soon now. And hopefully that work on singularity will lead to some better workload ideas about what transactions look like, and confirm whether we're optimizing the right cases or whether there's other uses that we need to do. But hopefully this provides a way of trying to break the chicken and egg problem that exists with development PC. And the current goal for the next few months is to make progress on the optimization work to improve some of the runtime overhead, and then write that up in November. So as I said, I've got some more results not in the slides here. I'm around this afternoon, so I'd be interested in talking to anyone about that. If there are questions.
I'm not clear why some of your optimizations are sound. For example, imagine you have an object of some type which has an invariant operation, unitomic blocks. So it's field A and field B are always the same. Now, a program entering an atomic block and running within an atomic block can see A and B be different, and therefore can do arbitrarily funny things. Now, one of those is plotter memory. That's okay. You're taking care of that. And nothing, for example, is true forever.
Why can it see?
Because other people are just doing writes to the heap and it's reading them. That is now, if this happens, because it's a listed reading of those, its operation will eventually, of course, assuming that it doesn't, for example, loop forever, or raise various exceptions, or do, perhaps other bad things.
Right. Yeah. That's another thing we need to do then, which is to put partial test validation on the back end of the program, so that it then ever and never tries to commit that it will do the test.
And perhaps doesn't even do more reads or writes.
That's right. In earlier work, we put that validation step in the transactional memory operation, and crossed our fingers that we'd be doing transactional memory operation. Of course, that becomes less plausible that all of these operations are transaction local objects. You don't go through the interface to deal with the
And similarly, one could raise runtime exceptions, and other things could go wrong.
The case of exception is one that we already do. When an exception needs to be found in the slot, it validates the transaction there.
Yes.
If it's valid, then we know the exception really ought to be invalid.
But there are other ways things can go wrong, do you know of, or that's just
well, the other ways I know of are, it could have various kinds of failures when one is like off the up. It could kind of tool track
or allocated code lines.
So it would need to be hardened against those.
But it shouldn't be anyway.
Right.
Deal with deadlocks.
So we don't have a problem with deadlocks, because if one thread tries to open an object for update and it's already open something else, then at the moment the second thread just walks into transaction to the end. That would be a case where we do some really sometimes dependency management to although we avoid deadlocks, we need to provide them as well. We don't have anything in the implementation of
Is it not a transaction aborting occurrence to try to open an object for read that's already owned for update by a transaction?
And that's another issue where it would be good to revisit what the performance is.
How is it now?
At the moment, there is any test when you open an object because that reduces powers of the task.
Is that exactly the thing that causes it to be possible to observe the object in an inconsistent state?
No, because you also mentioned race conditions. You'd have to atomically check it, and that would be incredibly expensive.
You have to atomically check if somebody already had it open.
Whatever else, like the race condition and having it open or something. I mean, this would be a fine optimization, but it's only an optimization only goes your hand.
And there's some work that I think more certainly Microsoft or Sierra did, but they looked at a lot of the design choices, and these made from this style of system what they term visible reading. So writers don't know about reading up to systems where you have proper multi-read writer. And they saw cases where one was read where the other was read, and in their work dependency management is driven by trying to find dependency management schemes that work well across all of those cases. There's a hybrid idea to be thought about well, perhaps to avoid having to test every time you open an object. That would be deferred until you fill up the chunk of the log, so that short transactions you don't detect it early. So that's massive for the transaction short that you've done quickly. But for long transactions, you
use the log size as a proxy for the complexity.
And
it's a good proxy.
Beyond a certain stage, that often starts to sophisticated things to use in a way that other threads would. So that short-running transaction-based update doesn't bother a long-running transaction to use. From the correctness point of view, we can use all these stuff before we what was the performance.
Any other questions? Let's thank Tim again.